Okay, so in a previous lesson, we have defined what a limit of a function is, and we have seen that limits are calculated at the open bounds of the domain in order to study the behavior of the function at these restricted points or at the infinite bounds of the domain. We have, in fact, introduced and calculated limits using table of values in order to observe the pattern that the values of y approach when x approach their corresponding values. Now over here we're going to discuss limits graphically. So based on the given graph, we're going to first point out the values of x that are restricted for the function, that are outside the domain of the function, and then study the limits of the function at these restricted values. So first of all, if we look at the graph that is given, we have, of course, the infinite bounds. So we have negative infinity and positive infinity at x. And then looking at the restricted values, we notice here that at -4, we have a hollow point. So that is a point that is restricted from the curve. So that is one of our restricted values. Then we have here x equals to 2, which is a vertical asymptote. So over here, x equals to 2 is also a restricted point. It is outside the domain of the function. And we notice here that the function at x equals to 0 is breaking. It's not continuous. So even though we do have a full dot here and 0 has an image by f, however, the function is not continuous there. So it requires us to find a limit. So over here, the limits that we need to find are the following. We have the limit when x is approaching negative infinity and positive infinity. We have the limit at -4, the limit at -2, and the limit at 0. I'm not sure why the limit at positive infinity is written twice. But anyway, so let's just first look at the limits at negative and positive infinity. Now, reading limits of a graph is the same as reading the coordinates of a point on a graph. So for example here, if I had this function where over here you have this point of abscissa 1, and I'd ask you to find its corresponding value of y. I'd ask you to find f of 1. So in order to find f of 1, what you would do is project x equals to 1 parallel to the y-axis and read its corresponding value of y, which assume in this case is a 2. So you tell me f of 1 equals to 2. Finding limits graphically is exactly the same thing. So over here, if we were to look at negative infinity, it's as if I have an ordered pair of abscissa negative infinity, and we need to find its corresponding value of y. So what we do is the same. So by projecting on the curve parallel to the y-axis, we notice that the curve would actually keeps on going infinitely towards a negative infinity on the y-axis. So over here, if x is negative infinity, y is also negative infinity. So, but we've already discussed in the previous lesson that we cannot write an ordered pair or write as f of negative infinity equals to negative infinity when we're dealing with infinite bounds or restricted values. However, we could still use it in order to understand the concept. So over here, when x is negative infinity, y is negative infinity. So the limit when x is approaching negative infinity of f of x is negative infinity. So again, you notice that as you project on the curve and read the corresponding value of y, since the curve here keeps on going infinitely downwards, then when x is negative infinity, y is also negative infinity. However, if we move to positive infinity, so over here, similarly, if x is positive infinity, what is the corresponding value of y, or at least which value of y is the function approaching. So as we project on the curve, we notice that we have y equals to -3 here as a horizontal asymptote, where the curve keeps on approaching a y equals to -3 infinitely without really touching it. So the value of y we're looking for here is -3. So the limit at positive infinity of f of x is -3. So these are the limits corresponding to the limits at negative and positive infinity. Now let's just tackle the restricted values. So over here we do have a restricted value at x equals to -4. So in order to determine the limit at -4, just similarly to what we discussed in the previous lesson when we introduced limits, we said that whenever x is approaching a finite value, now that finite value could be approached either from the left or from the right. So in order to determine the limit at -4, I need to determine the limit to the left of -4 and the limit to the right of -4 and compare them. If they are equal, then the limit at -4 is equal to them. If they're different, then the limit at -4 does not exist. So over here, I need to find the limit when x is approaching -4 minus, which represents the limit to left, and the limit when x is approaching -4 plus of f of x, which represents the limit to right. So over here, eventually, after we find these two limits, we compare them. Okay, if they're equal, then the limit at -4 is equal to them. If they're different, then this limit does not exist. So over here, how do I determine graphically the limit to left and the limit to right? So I start first by drawing x, the vertical line x equals to -4. And the purpose behind doing that is in order to separate the parts of the curve corresponding to the left of -4 and to the right of -4. So by drawing that vertical line, you'd notice that I do have this curve to the left of -4, and I have this curve to the right of -4. So in order to determine the limits to left and right, I need to find the value of y corresponding to x equals to -4 using each of these two curves. So over here, if I look for the image of -4 on the blue curve, which corresponds to the right part of the curve. So if we just look at the blue curve, ignoring the red one. So over here, we'd in fact have for x equals to -4, we have y equals to a -1. So here, this limit is -1. However, if we look at the curve to the left of -4, so which now we're looking at the red curve only. So as we project at from -4 to the curve and we read the corresponding value of y, you notice that the red curve also has y equals to -1 when x is 4. So over here, this is also equals to -1. So the two curves being equal, in that case, this limit, which is the limit at -4 of f of x, is also equals to -1. It would be equal to them. However, if we were to do exactly the same thing, now this is x equals to -2. Now there's supposed to be a negative here. So now the vertical line x equals to -2 is already drawn. So all I have to do is just point out the parts of the curve to the left of -2 and to the right of -2. So again, if you're using red for left, so if you'd look at x equals to -2, you notice that this is the part of the curve to the left of -2. Now, this was the part that was to the right of -4, but now that same part is to the left of -2. And similarly, we'd have this part to the right of -2. So again, in order to find the limits to left and right of -2, we'd have to find the value of y corresponding to -2 on each of these two curves. So over here, if we look for the limit to left. So this is the left part of the curve, which is to the left of x equals to -2. So when x is -2, as you project on the curve, you'd notice that the value of y is -infinity. So the limit when x is approaching -2 minus of f of x is -infinity. However, if you look to the limit to right, if you look at the part of the curve to the right of -2, you notice that when x is -2, y is also -infinity, because this curve also keeps on going down further to -infinity as x is approaching -2. So over here, the value of y is also -infinity on the blue curve, so which leads to the limit when x is approaching -2 plus of f of x equals to a -infinity. Now again, comparing the limits to left and right, they are equal. They're both equals to a -infinity. Then the limit at -2 is equal to that. Now if we were to do the same thing at 0, so again, we need to point out which part of the curve is to the right and to the left of 0. So over here, this part of the curve, this is x equals to 0 here. It's the y-axis. So we notice we do have this part to the left of 0. And we also have that is the part of the curve to the left of 0. So if we were to read the value of y corresponding to x equals to 0 on each of these two curves in order to determine the limits to left and right. So looking at the left curve, the curve which is to the left of x equals to 0 now. So over here, you'd notice on this left curve, when x is 0, y is 0, and that is that point, in fact. So the limit when x is approaching 0 minus of f of x is, in fact, 0, because on the left curve, when x is 0, y is 0. So the limit to the left of 0 is, in fact, equals to 0. However, if we look at the right curve, which is this one. So over here on this curve, when x is 0, y is 2. So the limit when x is approaching 0 plus of f of x is equal to 2. So now that we have found the limits to left and right, we compare them. We notice that these two limits are different, which leads to the limit of 0 doesn't exist. So the limit when x is approaching 0 of f of x does not exist. Now, if the limit at 0 does not exist, but it doesn't mean that the limits to the left and right don't exist. They could exist, but they could actually be different. And we have discussed in the previous lesson that when the limits to left and right are different, the curve around that point to the left and to the right of that point would actually be located at different places, and this is why the limit would not exist, but it would have a limit to left and a limit to right. So to recap, finding limits graphically is the same thing as finding the value of y corresponding to a given value of x, the same way you do for any function. If you're given the value of x, you just project on the curve parallel to the y-axis and read the corresponding value of y. But however, whenever we're dealing with restricted points or infinite bounds, it would be maybe a little bit more tricky, but the concept is the same. So you look at that value of x, you project it on the curve to actually see the behavior of y there in order to read the value of y and determine your limits. Now, before we wrap up this lesson, I need to go through more details regarding asymptotes. Now, in the previous lesson, we have introduced them briefly, and we have already spoken about asymptotes here at x as x equal to -2 and y equals to -3 being asymptotes to the curve. Now, however, in the previous lesson, we have briefly defined that an asymptote is in fact a straight line that the curve keeps on approaching but never touches. So usually that happens whenever, for example, here, if we were to start with the horizontal asymptote. Now, an asymptote could be horizontal, it could be vertical, and it could be oblique. Now, we're going to tackle horizontal and vertical asymptote. The oblique asymptote, we're going to tackle it in the next lesson. Okay, so so over here, just as we refer back to the previous example, you'd notice that y equals to -3 is a horizontal asymptote because the limit at positive infinity was equal to -3. So at positive infinity, having the function having a limit of -3, it means that the curve will keep on going downwards and approaching y equals to -3 without ever touching it. So that is why y equals to -3 is an asymptote. So going back here, in order to generalize that, you'd eventually have a horizontal asymptote when you're finding a limit where the value of x is infinite and the value of y is finite. So over here, since the limit, the value of the limit corresponds to the value that y approaches. So whenever x is approaching an infinite value, whether positive infinity or negative infinity, if y is approaching a finite value, then y equals to b would actually be a horizontal asymptote. So in order to put that into perspective graphically and discuss all the possible cases you could eventually get. Now over here, if this is the horizontal line, y equals to b. Now in case you have the limit at positive infinity, so limit at positive infinity, it means that the curve approaches y equals to b at positive infinity. And in case the curve is located above the line y equals to b, then in that case, y would in fact be slightly greater than b, and greater than b would mean that the limit would be plus. Similarly, if we're still at positive infinity, if you're finding the limit when x is approaching positive infinity, it means that y is approaching b at a positive infinity on this side of the coordinate system. However, if the curve is approaching b and the curve is below the line y equals to b, it means that y is smaller than b. Over here, y was greater than b because the curve was above the line y equals to b, while here y is below the line y equals to b. So this is why the limit is b minus, because y is smaller than b. Now, similarly, if we were to be finding the limit at negative infinity. Now, if x is at negative infinity, then you'd notice that the curve would actually be approaching y equals to b on the left side of the coordinate system at negative infinity. And again, if you have y greater than b, if the curve is above the line y equals to b, then in that case the limit would be b plus. While if the curve is below the line y equals to b, it means that y is smaller than b, so the limit would be b minus. So again, whatever the position of the curve is, whether it's above or below the line, whether it's at negative infinity or at positive infinity, whenever you have a limit where x is infinite and y is a finite value, in that case, y equals to b would be your horizontal asymptote. However, if we had it the other way around, now if x is approaching a finite value while y is approaching an infinite value. So in that case, x equals to a would be your vertical asymptote. So over here again, discussing all the possible cases you could actually have. So again, whenever we are finding a limit when x is approaching a could be could be approached from the left and from the right. So by drawing the vertical line x equals to a, in that case, if you would be working to the left of a, so to the left of a, which means that x is smaller than a. So whenever you're working to the left of a, since the value of y here is infinite in order to have a vertical asymptote, then in that case the curve at a minus could be either a positive infinity, it could be approaching x equal to a from the top, or from the bottom at a negative infinity. So in this case, the limit at a minus is positive infinity. In this case, the limit at a minus is negative infinity. And similarly at a plus, when x is approaching a plus, x would actually be greater than a. So the curve would be located to the right side of a. So again, you could have two cases. The curve could be at the top going towards positive infinity, or at the bottom going towards negative infinity. So in that case, when x is approaching a plus, in this case the limit would be positive infinity when the curve would be going upwards infinitely, and it would be negative infinity when y is going upwards infinitely, or when y is going downwards infinitely. Now, in our next lesson, we're going to be discussing finding limits by replacement or algebraically, and then later on generalize to finding oblique asymptotes. Now, similarly to having horizontal or vertical asymptotes, could sometimes be oblique. So in future lessons, we're going to be discussing oblique asymptotes, and we're going to also be discussing how to evaluate a limit algebraically. It means that if you do not have the curve of the function, how could you find the limits of that function at the open bounds of its domain using the equation of the function.